Finally, what does a non-standard Gaussian look like? Okay, so if you have, instead of a standard Gaussian, you have a Gaussian with mean of mu and variance of sigma square. Remember, the first one is the expected value, the second one is the variance. So if x is a standard Gaussian, you scale it by sigma and you shift it by mu, which means you define random variable y as sigma times x plus mu, then that random variable y will have a Gaussian distribution with a mean of mu and sigma squared. Okay, we didn't talk about transformations and functions of random variables yet. That is in module 3, if you remember. So this will be much more easier to grasp for you when we talk about those. But for the time being, let me just state that when x is a standard Gaussian and y is defined in this way, then what you get is a Gaussian which is not standard. It has a mean of mu and standard deviation of sigma. Well, I have given them here, but if you take these integrals, you will obtain these results. But in general, writing them through this relationship is much more easier, as we will see later on in the course. The PDF is given in this way. Mm, Compare this with the standard Gaussian PDF, 1 over square root 2 pi times e to the power minus x squared divided by 2. So what you have here is, instead of y squared, you have y minus mu squared. And here, instead of 2, you have 2 times the variance. And here, you see the standard deviation. Sometimes you also see this as 2 pi sigma square inside the square root, because sigma square by itself is the variance. So sometimes you use the standard deviation if you have it, or you use the variance if you have variance. Okay, depends on your choice. And of course, if you take these integrals, the mean, expected value of y, and expected value of y minus mu squared, that is the variance, you will see that the mean is actually equal to mu, and the variance is actually equal to sigma squared as expected. Now finally, I will give the characteristic function of the Gaussian distribution with the general setting of expected value mu and variance sigma square. Obviously, this is the definition. Well, this part is the PDF, and you just have e to the power j omega y, which is the function you are computing the expected value for. And again, you can merge this with this exponential term. Again, it's not that difficult to take this, but it is a little bit tedious, so I'm not going to give you every step. The result, it turns out to be e to the power j omega mu minus omega square sigma square over 2. So of course, mu here is the mean, sigma square is the variance. And if you apply this to a standard Gaussian with mu equals 0 and sigma square equals 1, you get from this the characteristic function of random variable x, which is standard normal, turns out to be e to the power, well, this term will vanish because mu is 0, and this one will be 1, so that is e to the power minus omega square over 2. Okay, and what about probabilities? Obviously, probabilities are related to the CDF, and if you have, well, we define those here. Okay, the CDF of standard Gaussian is given by phi x, and the complementary CDF is q of x. But if you have a non-standard Gaussian, right, with mean of mu and variance of sigma square, obviously you can go the other way here, and obviously y is equal to x minus mu divided by sigma. Therefore here, to compute the probability that random variable y, which is non-standard Gaussian, is less than or equal to y, you can use phi with the parameter of y minus mu divided by sigma. Okay, and the complementary event, the probability of y exceeding y equals q function evaluated at y minus mu divided by alpha. So that concludes our discussion of the Gaussian random variable for the time being, because, well, the Gaussian random variable, as you might know, is a very, very significant, a very important random variable. We will revisit Gaussian uh, and we will examine its properties, and we will talk about why it is this important when we talk about the central limit theorem, obviously. Okay? And one final note, obviously, the predefined or important distributions are not confined to this list that we have done in this class. There are many more distributions that we could have discussed, but we have limited time. I'm not going to give everyone, but of course, Stephen Kay's book and others, of course, describe some others, and you can find information online. Some of them are used in certain situations, in certain contexts, and some of them are used more in certain disciplines or in certain applications, but we cannot do them all. But we will talk about them in class.